Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. I post videos with solutions of practice problems at smarturl.it/pass actuarial exams. Here's some information about online seminars that I teach for exams PFM, IFM, and LTAM, and study manuals that I wrote for those exams, PFM, IFM, and LTAM. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to offer a tax-deductible donation to support our students, please go to smarturl.it/help ISU actuary. This is problem number 3 from the last exam LTAM from October 2018. The Lee-Carter stochastic mortality model assumes that the natural logarithm of the central death rate m of xt follows a discrete stochastic process that this I usually write ln for natural logarithm. The problem itself on the exam wrote it as log. So log of m of xt is alpha x plus beta x times kt, where x is the attained age, t is the calendar year, and alpha x and beta x are age-dependent parameters. You are given that k sub t is k sub t minus 1 plus c plus sigma k zt, where zt are independent, identically distributed standard normal random variables. You're also given that for a log normal random variable y with parameters mu and sigma, e of y to the k is e to the k mu plus 1/2 k squared times sigma squared. Part A asks us to define the central death rate, mx, in terms of the force of mortality and survival probabilities. Part B tells us that we are given that alpha of 80 is minus 2.4, beta of 80 is 0.05, k of 2017 is negative 4, c is negative 0.2, and sigma k is 1.5. And part 1 asks us to calculate the mean of m of 80 in 2018. Part 2 asks us to calculate the standard deviation of m of 80 2018. Part 3 asks us to calculate the 10th quantile of m of 80 2018. Part C tells us to assume uniform distribution of deaths between integer ages, and we asked to, in part 1, show that 1 minus 1/2 mx divided by 1 plus 1/2 mx is equal to px for integer x. Part 2 asks us to calculate the median of p of 80 2018, the 1-year survival probability for an 80-year-old in 2018. Part D says, criticism of the Lee-Carter model is that it can give a poor fit to population data. State 2 common features of population mortality that are not captured in the Lee-Carter model. Well, the central death rate is defined as qx divided by the integral from 0 to 1 of tpx dt. And that's the same as the integral from 0 to 1 of tpx times mu x plus t dt divided by the integral from 0 to 1 tpx dt. Or you can also write it as the integral from 0 to 1 of lx plus t times mu x plus t dt divided by the integral from 0 to 1 of lx plus t dt. Or as dx divided by the integral from 0 to 1 of lx plus t dt. And it can be viewed as a probability-weighted average force of mortality between ages x and x plus t, or number of deaths observed divided by the exposure to death, as opposed to qx, which is calculated as the number of deaths observed divided by the initial population size at the beginning of the year. For part B, we have the natural logarithm of m of 80 2018 equal to alpha of 80 plus beta of 80 times k 2018, which is the same as alpha of 80 plus beta of 80 times k 2017 plus c plus sigma k times z 2018, by definition of how this model is done, strictly from its description. And we are given that alpha of 80 is negative 2.4, beta of 80 is 0.05, k 2017 is negative 0.4, c is negative 0.2, this is the constant drift term, and sigma k is 1.5. This parameter is the standard deviation of the annual change in kt. And it's a very strange notation the way it's written, but that's the notation in the study note, that's the notation in this problem. Therefore, the natural logarithm of m of 80 2018 is negative 2.4 plus 0.05 times negative 4 minus 0.2 plus 1.5 times z 2018. And if you just do the algebra and calculate it, this becomes 0.075 z 2018 minus 2.61. And the model assumes that zt, every zt, including z 2018, where t is equal to 2018, is standard normal. Well, if so, then the natural logarithm of m of 80 2018, which is 0.075 z 2018 minus 2.61, is normal with mean 2.61 and variance equal to 0.075 squared. So we basically know now that m of 80 2018 is log normal with parameters mu equal to negative 2.61 and sigma equal to 0.075, and therefore the expected value of it is what we get when we plug in those parameters in the formula for the expected value of a log normal random variable, in this case e to the negative 2.61 plus 1/2. So the expected value, it's e to the negative 2.61 plus 1/2 times 0.075 squared. And that's approximately equal, well, you can put 1 squared in front of this 0.075 squared, but you don't really have to because 1 squared is 1. So that's approximately, we calculate to be approximately 0.073741651. What is the second moment of it? Well, the second moment is e to the minus 2 times 2.61 plus 1/2 times 2 squared times 0.075 squared, and that's approximately 0.005468505. And the variance is the second moment minus the square of the first moment, and we calculate it to be approximately the square of 0.0553841 squared. 3841, the square of that number, The natural logarithm of m of 80 2018, therefore, is normal with mean negative 2.61 and 0.075 squared variance. And we have these parameters of m, but we ask the question now about the 10th percentile of the distribution. And the 10th percentile of a standard normal distribution is negative 1.282, according to the table, the standard ultimate life table given on the test. Therefore, the 10th percentile of the natural logarithm of m of 80 2018, which is an increasing function of the corresponding normal random variable, because the natural logarithm is an increasing function, is e to the minus 2.61 minus 1.282 times 0.075, and we calculate that to be approximately 0.0671047.8. For part C, part 1, recall that under UDD, TQX is T times QX. That's like the defining property of UDD. If you have a hard time memorizing things, you still can remember this. And this is so important to remember. So remember this for the test. And therefore, mx, which is qx divided by the integral from 0 to 1 of tpx dt, is the same as qx over the integral from 0 to 1 of 1 minus tqx dt. And under UDD, this is qx over the integral from 0 to 1 of 1 minus tqx dt. And we calculate the integral, well, basically it's a linear function of t. And this comes out to be qx over 1 minus 1/2 qx. When I was taking the exam on life contingencies, we were actually expected to have memorized this. But, when I was taking the exams, you had to walk 10 miles to the exam center in a snowstorm, uphill both ways. The exams were much harder then. But anyway, the mx, therefore, is also can be written as if you multiply both sides by 1 minus 1/2 qx. So mx is qx over 1 minus 1/2 qx, multiply both sides by 1 minus 1/2 qx, so the left-hand side becomes mx minus 1/2 mx qx, and then leave that mx on one side, move the other stuff to the other side, so this becomes mx is equal to qx plus 1/2 mx qx. So that's qx times 1 plus 1/2 mx, so that qx is mx over 1 plus 1/2 mx. And px is 1 minus qx, so 1 minus what we just calculated, and that is equal to 1 plus 1/2 mx over 1 plus 1/2 mx minus mx over 1 plus 1/2 mx, and this becomes 1 minus 1/2 mx over 1 plus 1/2 mx. Again, that's something that we were once expected to memorize. For part C, part 2, we are now studying P of 80 2018, the one-year survival probability for 80 in 2018, for an 80-year-old. The survival probability is a decreasing function of the central death rate. Therefore, in general, so the central death rate, the rate at which you're being killed, goes up. Obviously, survival probability goes down, right? So in general, P quantile of P, whatever, P, that's bad choice of notation, I must admit. Whatever quantile we're talking about for P of 80 2018 corresponds to 1 minus P quantile of M of 80 2018. In this case, we're looking for the median of P of 80 2018, and this corresponds to 1 minus 0.5, so 0.5, so median of M of 80 2018, and the median of the corresponding normal distribution. Okay, well, what's the median of standard normal distribution? 0. So the median of M of 80 2018 is e to the 0.075 times 0 minus 2.61. So this is e to the minus 2.61, or approximately 0.07353,454. And the median of P of 80 2018 is what you get when you replace the value of M by this value, e to the minus 2.61. So 1 minus 1/2 e of minus 2.61 over 1 plus 1/2 e to the minus 2.61, and that comes out to be approximately 0.907324. So the study note says, indeed, that the most important thing about this model is that the fit to data tends not to be very good. This is partly because it does not allow for any cohort effect, and cohort effect is how mortality is affected by the year of birth. But we often see cohort effects in the actuarial and population data. Also, the model implicitly assumes perfect correlation between mortality improvements at different ages, but the mortality data shows that improvements may be far from perfectly correlated. So these are the two facts, actually the two facts as listed in the study note. This is what the study note says. They're similar, really, but both of them indicate that the fit is not very good. Please remember this is copyrighted material. The problem itself comes from a Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.